If you're worried about the current progression of AI, then you definitely should be concerned with the next frontier in computing: quantum. Quantum computing is touted to be so powerful that it would have the capacity to hack secure encryptions in seconds. Your personal data, your bank account, government databases, and even supposedly unhackable recent innovations like cryptocurrency will not be safe from the power of quantum. And with chips like Microsoft's Majorana 1 and Google's Willow, this concept is quickly becoming a practical reality. However, there's a flip side to these dark security concerns, predominantly highlighted in healthcare. Leading companies are claiming that quantum computing will be able to solve a number of health issues, create new and more targeted drugs and antibiotics, cure cancers, and maybe even provide the solution to biological certainties like aging. But what actually is quantum computing? How does it work? And how close are these corporations to making this science fiction sounding tech a reality? Conventional silicon-based computers use bits as a unit to store information. Over the years, the capacity to store and process information has reached the exascale levels of operations per second. This is made possible with large amounts of memory storage capacity running in petabytes. Quantum computers leverage the laws of quantum mechanics to encode exponentially more information in their storage units, referred to as quantum bits or qubits. Quantum computers and the qubits they use can be made from a range of materials and not just silicon alone.
Qubits are like our classical bits, right? These are essentially zeros and ones in a transistor. And we need the analog of that in quantum computing. The analog is a qubit, a quantum bit, that serves as that core information unit. It's where we store the information and then we process on those qubits to create computation and ultimately, get solutions back out.
This removes the limitation on information storage that comes with using silicon. In the case of classical computers, a bit can occupy only one or two states, on or off, 0 or 1. Conversely, qubits can occupy a weighted combination of 0 and 1 at the same time. This unique ability of qubits is called superposition, and opens up a realm of possibilities when it comes to processing data in quantum computers. When qubits in superposition are combined, they can be scaled exponentially. For instance, 2 qubits can compute with 4 pieces of information, 3 with 8, 4 with 16, and so on. The larger the number of qubits used in a quantum computation, the greater is the capacity to process information. Therefore, researchers aim to make quantum computers with a large number of qubits. It is estimated that the quantum computer that will compute a revolutionary discovery would need at least 1 million qubits. Much like during the infancy of classical computers, a quantum computer built today occupies large amounts of space. Operation of a quantum computer involves using several instruments that occupy the bulk of this space. The computational area where the qubits lie barely occupies the space of a fingernail though. This is because, to leverage the quantum properties of matter, scientists need to operate at atomic scales. Qubits can be made by applying a wide variety of quantum systems such as atoms, photons, ions, and more. However, one of the most commonly used approaches is that of the superconducting circuit. A superconducting qubit consists primarily of a tiny loop of metal wire designed to behave like an atom. To achieve this, the metal loop is cooled to temperatures close to absolute zero, minus 273 degrees Celsius. These temperatures can be reached with the help of a dilution refrigerator, something that is about the same size as a household refrigerator, but extremely expensive to buy and operate. At these nearly zero temperatures, metal loops or wire can occupy 2 states, one at lowest energy level or ground state, and the other at a higher energy state. The 2 states can be initiated using microwave pulses. Companies like Google and IBM have adopted this approach to build their quantum computers. While Google is using the commonly available aluminum to make their superconducting qubits, IBM is using a mix of aluminum and niobium. The approach might sound like a cost-effective way to build the next quantum computer, but the real costs lie in cooling these atoms to superconducting temperatures. Currently, these companies can only support a few hundred to 1,000 qubits using their dilution refrigerator. However, as the quantum computer scales up, bigger dilution refrigerators will need to be built to make larger numbers of qubits work together. A trapped ion qubit is another method which completely avoids the dilution refrigeration requirement. In this approach, the charged molecule or ion is trapped, where it behaves like a tiny bar magnet. The operation of the ion can be manipulated using a thin laser beam, and they are used as two possible quantum states for the qubit, up and down. Multiple companies have adopted this approach to overcome the challenges of superconducting qubits. The setup of such a quantum computer looks more or less the same. It consists of a computing chip that is the size of a dime, a large vacuum cylinder that operates around the chip, a laser that manipulates the qubits, with a detector in place to read them. The chip acts like a trap for the ions, which can either be calcium or a terbium. The laser performs the dual role of cooling down the chip and operating the qubits as they occupy their position inside the vacuum chamber. A unique property of the qubit is that observing it or taking a reading ends its superposition state and brings it to a defined state of 0 or 1. The ability of a qubit to remain in superposition state is known as coherence and is crucial to allow quantum operations to occur. In the case of trapped ion qubits, the vacuum chamber ensures that they do not interact with air particles that could potentially end their superposition state. This increases the coherence time of the qubit to minutes or possibly even hours. In contrast, a superconducting qubit has a coherence time of a few microseconds or milliseconds. While this is a major improvement over the nanoseconds of coherence time that was initially achieved with these qubits, it is still small compared to the trapped ion qubits. While this works well for quantum data storage, long coherence times impeded interactions between qubits, thereby increasing the amount of time required for quantum computations to occur. Much like superconducting qubits, trapped ion qubits also have a scalability problem, where each chip can only contain a handful of ions at a time. Increasing this to millions of qubits needed for a quantum computer also requires working on the capacity of vacuum chambers to hold a large number of qubits while also making them interact. To overcome these challenges, a third type of qubit has been developed, called a neutral atom qubit. Researchers working in quantum computing will agree that atoms are nature's perfect qubits. While the nucleus of the atom holds a positive charge and electrons hold a negative charge, an atom is a neutral overall. However, shining a light on the atoms can increase its energy level, which can serve as an on or 1 state, with its ground state serving as the 0 or off. Lasers also serve as optical tweezers to hold atoms in place and suppress their movement, which helps in reducing their temperatures to near absolute zero. Here, the energy levels of the atoms can be manipulated using light and coherence times of over 1 second, and even more can be achieved. The greatest advantage of neutral atom qubits, though, is that it allows the creation of qubit arrays by holding a large number of neutral atoms in place by shining a laser through a lens. Using advances in lenses and lasers, the number of atoms controlled in this fashion can be scaled easily. The shortcomings of this approach is the slow rate of computation. While it's comparable to computations achieved with trapped ion qubits, the neutral atom qubit system is far slower than the superconducting qubit system. Moreover, operating neutral atoms is much more tricky, requiring a complex set of calculations to hit each atom to take its necessary quantum state. More recently, a new type of quantum system is being developed to make qubits photons. As the name suggests, these qubits are encoded by the quantum state of light. Since light is made up of photons, researchers use various quantum states of photons such as polarization, path, frequency, or time-bin encoding to process quantum states. Just like the development of classical computers is incomplete without the internet, quantum computers built without connecting them to other quantum computers would lock down the true potential of these magnificent machines. This is why work is also going on developing quantum networks, and photon-based qubits are ideal for deployment in such a network. Photons are ideal as qubits since they can travel long distances without significant loss of information, something we have experienced in fiber optic networks that operate already. An equally important aspect of photons is that they are immune to environmental disturbances and can maintain their quantum state over longer periods. This facilitates long coherence times for quantum data, allowing both long-term data storage as well as computation with photonic qubits. Unlike superconducting or trapped ion qubits, quantum states can be assigned to photons using simple devices like beam splitters and phase shifters. While a lot of focus has remained on the type of qubits used for quantum computations, qubits are just a small part of the bigger puzzle. Qubits use their quantum state to store information. However, it is the quantum algorithm that takes the computational ability of quantum computers to a level much superior than the fastest supercomputer. Much like the classical algorithm that instructs the computer in a step-by-step manner to solve a problem, a quantum algorithm using principles of quantum mechanics instructs a quantum computer to carry out computations to certain problems in a far more efficient manner than possible with a classical computer. Quantum algorithms are designed to leverage quantum properties of qubits such as superposition and entanglement to perform parallel computations on possible inputs simultaneously. This parallel processing, while using qubits that can store more than one information state at a time, gives quantum computers a superior computational ability over classical computers. A quantum algorithm is deployed in a typical quantum circuit where qubits are input with certain information and it concludes with a measurement. A quantum circuit also includes quantum gates, which act on a limited number of qubits. Designing a quantum algorithm is a complex task that requires a thorough understanding of computational theory and quantum mechanics. There are only a limited number of quantum algorithms that have been developed so far, and each is recognized by a name or the type of computation that it helps accelerate. Popular among them is Shor's algorithm that allows factorization of large numbers, which has proven difficult and time-consuming for classical computers. This also poses a threat to one of the most commonly used encryption systems for data transmission, the RSA crypto system. Another popular quantum algorithm, known as Grover's algorithm, helps speed up search in unstructured databases. While classical computers deploy a linear search pattern to such a request, a quantum computer using Grover's algorithm can achieve the same in time proportional to the square root of the number of the items in the database. The Deutsch-Jozsa algorithm can determine whether a function is constant or balanced with a single query, providing answers significantly faster than classical computers. Although in their infancy, quantum algorithms are helping us to understand the fundamental nature of computation and the connections between physical and computer science every time a new algorithm is developed. However, deploying quantum algorithms on quantum computers also comes with its own set of challenges due to issues such as decoherence and error rates, prompting the need for quantum error correction. Coherence is an important property in qubits, which allows them to remain in their superposition state. We know that quantum computation continues only while the qubit is in superposition and ceases when it returns to normal state. Decoherence is the process where a qubit loses its superposition state. This can occur due to varied factors, but largely results due to interactions with their surroundings. As discussed earlier, qubits are extremely sensitive, and changes in factors such as electromagnetic fields, temperature, or vibrations can disrupt their quantum state. This can bring quantum computations to an abrupt halt, preventing them from being completed. This can lead to errors in quantum computations, since information stored inside qubits is lost. In the long run, this can also prevent the deployment of quantum computers for real-world applications. This is why researchers are working on strategies to increase coherence times of qubits, while also ensuring that errors generated during these calculations are quickly rectified through error correction strategies. Quantum error correction, QEC, works on creating redundancy. Instead of storing quantum information on a single qubit and risking loss to decoherence, researchers store data in multiple qubits to spot errors when it occurs. Not only does this prevent loss of information, it also opens up the possibility of detecting the errors and correcting them while computations are still running. This allows qubits to remain in their superposition state, increasing coherence times and bringing quantum computation closer to real-world deployment. The most common method of doing so is using a logical qubit for computation. A logical qubit is an abstract concept where multiple physical qubits are grouped together and treated as one unit of information storage and processing. Inside a logical qubit, the physical qubits are entangled with each other. Quantum entanglement is a phenomenon exclusively seen in quantum mechanics, where the quantum state of a particle in a group cannot be described independently of the state of others. This phenomenon is observed even when the two particles are not connected to each other and separated by a large distance. The great Albert Einstein referred to this as spooky action at a distance. Properties like quantum entanglement are being leveraged to build quantum networks of the future. However, this property can also help correct errors in quantum computations. When physical qubits are entangled to each other, researchers can deploy quantum error codes that can detect and correct errors in individual qubits without actually having to measure their quantum states. Using quantum error correction is a vital step towards development of fault-tolerant quantum computers, FTQCs. As companies and research institutes race to build quantum computers with large numbers of qubits, the increasing complexity of these systems and their size will introduce a large number of errors which need to be corrected. Common quantum errors that occur are changes in phase or bit, where the qubit enters the opposite quantum state than what is required to be stored in it. Quantum error correction codes such as Shor code or surface code can detect these types of errors and correct them without impacting quantum states. Deploying error correction further increases the overheads in quantum computing, since a larger number of qubits need to be included and precise control is needed to correct errors without disturbing quantum states of the physical qubits. This is achieved by first carrying out syndrome extraction, a process where auxiliary or ancillary qubits are measured to gather further information about possible errors inside a logical qubit. A quantum circuit is carefully designed to interact with the data of the ancillary qubits and measure them. The information extracted from them is called syndrome, which reveals if errors have accumulated. Through a process of decoding, syndrome data is analyzed to determine which set of errors have occurred. This is done with the help of classical algorithms that match syndrome patterns to various configurations. Highly efficient decoders run in real time to identify these errors with a high level of accuracy as well as speed in a bid to achieve fault-tolerant quantum computing, measured through quantum fidelity. In quantum computing, fidelity is used to quantify how close a quantum system is to running its intended state. When fidelity is high, quantum systems are robust and can rapidly identify and correct errors as they accumulate, while also determining which quantum algorithms can be executed towards building a fault-tolerant quantum computer. While the race is on to build quantum computers with a higher number of qubits, fault-tolerant quantum computers could help herald a future of quantum computing where less than 1 million qubits are required for groundbreaking discoveries. But the question remains, what groundbreaking discoveries can quantum computers really make? Interestingly, the answer isn't limited to one or two fields alone. Drug discovery and development is an extremely slow and expensive process. Earlier, much of this was achieved through trial and error, and although computational modelling has been deployed to improve the pace of this process, drugs need to also go through long clinical trials to demonstrate that they are safe. Metabolism of drugs inside the body is too complex a process for classical computers to simulate. However, an advanced quantum computer can compute this, since metabolism involves processes such as oxidation, which are inherently quantum, making quantum computers the right technology solution to approach these problems. Accurate modelling of existing molecules such as penicillin 2 need extremely powerful computers. A Boston Consultation Group estimate suggests that classical computers would need the number of bits shown as 10 followed by 86 zeros to achieve this. In contrast, a quantum computer could do this in a snap. Once deployed, quantum computers can potentially search for cures to diseases like cancer, Alzheimer's disease, and more in the future. A major problem facing humanity today is climate change. While efforts have been made to reduce emissions in a staged manner to minimize the impact of the warming planet, we will soon reach the point where radical solutions will be needed. Research efforts in technologies such as carbon dioxide sequestration have so far yielded solutions that are too expensive or energy intensive to deploy. If we find low-cost, low-energy demanding catalysts that trap carbon from the atmosphere, then we can delay the warming of the planet. Such computations are beyond the scope of classical computers currently, but could be a day's job for a quantum computer. Quantum computers can not just aid us in fighting climate change, but also recovering from its impact. As the world's population swells, there are increased pressures on the agriculture industry to feed the world. Fertilizer production is an energy-intensive process, carried out at high temperatures and pressures, and contributes approximately 2% of global carbon emissions. Alternative production approaches that could achieve the same output at room temperature and at a fraction of energy input have remained elusive for years, but quantum computers could find the necessary solution that could be deployed locally, further helping to reduce emissions. Our attempts to move away from fossil fuels have only taken us this far, where we have deployed large-scale solar and wind power plants. Not just existing technologies, but quantum computing can also help research improvements in upcoming approaches. The National Ignition Facility, NIF, set a record in December 2022 by producing nuclear fusion plasma that generated more energy than was put in, promising a future of nuclear fusion technology. Replicating processes that occur on the Sun, scientists are hopeful that they can combine hydrogen atoms to yield non-radioactive helium and tons of emission-free energy that can power the world. Making the fusion plasma to initiate the fusion reaction and maintain it inside the reactor for continuous production of energy have proven challenging so far, and faster computational ability of quantum computers could help accelerate the process. If discovery of cancer-curing drugs or nuclear fusion energy seems like far-fetched goals, then here's something quantum computing could impact right away: finance markets. It is not difficult to imagine that banks and financial institutions will want to access technologies that could help them predict how markets will behave and maximize gains for investors. Quantum computing companies and financial institutions are already collaborating to work out algorithmic approaches that can carry out valuation of financial products and also assess credit risks. Comparing performance on these models, which were also run on classical computers, the researchers found that quantum computers with as little as 50 qubits were able to accurately predict outcomes as they occur in the real world too. With 300 qubits, the performance could be bettered further and delivered to customers in the coming few years. Big names in industry such as IBM, JP Morgan Chase, and others are actively working on making this a reality, even as we have just begun to scratch the surface of possibilities with quantum computing. Superior computing capabilities of quantum computers have raised a primary fear that conventional encryption algorithms will fail as soon as quantum computers kick into action. If bad actors get their hands on quantum technology, they could wreak havoc on classical computation systems by breaking through encryptions and security measures with ease. Interestingly, the solution to the cryptography problem posed by quantum computers comes from quantum computers themselves. A new layer of security measures are being worked out as quantum cryptography leverages quantum mechanics to secure data transmission of the future. In such a system, a quantum key would be generated using photons between two parties engaging in data transmission. The two parties use polarizers to exchange their data, and the key would tell the receiver how to decrypt the message. Called quantum key distribution, QKD, this approach is highly effective since it also works naturally to prevent any eavesdropping attempts and block them. Much like the qubit losing its superposition state when observed or measured, the photons in a QKD would also change their polarization in case an eavesdropper tried to intercept the transmission. The recipient would become aware of the interception since transmission would no longer work with the same key. Although much of the focus has remained on how quickly quantum computers can compute and leave classical computers behind by years, there is also another major advantage of using quantum computers: optimization. A lot of problems that we face in the world today are not just about getting the right answers, but also about getting the most optimum answers. The traveling salesman is a popular problem, where a hypothetical salesman needs to travel to multiple cities, reaching them once and returning to the starting city. This has been difficult for classical computers to solve, but quantum computers rather specialize in researching solutions for these. Using quantum computers to solve this problem isn't just a demonstration of their computational superiority, but has real-world applications too. Organising traffic flows or using a fleet of buses to meet travellers' demand in the most fuel-efficient or time-efficient manner are optimization problems that administrators face every day. Quantum computing is poised to change that. Quantum computers aren't just a technology evolution of the classical computer, but a major leap forward in what humans can achieve using quantum technologies. The field will open up a myriad of new avenues for research and development and looks to completely change the world, hopefully for the better. Computing is about to go quantum, and we are here to witness it.
Remember to hit the subscribe button and ring that bell to stay updated with our latest content. And while you're here, why not check out another one of our exciting videos? Thanks for watching, and see you in the next one.